Welcome to my new calculus channel. My name is John Gabriel, and in today's video I'm going to talk about some really weird concept in mainstream calculus called a rate of change. There isn't any such thing as a rate of change, but as you'll see in a short while, exactly what they're telling you to do is something entirely different from what they think they're asking you to do. So I'll explain everything to you as we go along. Let's begin. So if you search for rates of change in calculus, you'll get a lot of videos. I chose this one here because this is a pretty popular one, Paul's Online Math Notes, and it's in this link here. So this is probably out of a first-year calculus course, and what they're teaching you here is how to use differentiation. And so let's look at the problem that's presented here. Two cars start out at 500 miles apart. Car A, which is here in initial distance, is to the west of car B and starts driving in a straight line towards car B at 35 miles an hour. And at the same time, car B, which is at this point here, starts driving south at 50 miles an hour. So far, so good. Now here comes the problem. It says, after 3 hours of driving, at what rate is the distance between the two cars changing? And is it increasing or decreasing? Well, first of all, every number is by definition a rate. Even a whole number is a rate. For example, 2. 2 is the rate of the magnitude denoted by 2, or measured by 2, and the magnitude measured by 1. And that's how you get to. You compare a length which is twice the length of the unit, the assumed unit. It doesn't have to be any particular size in this case. It can be any chosen size that you like. So a rate, by the way, is something that tells you a proportion. Okay, so if you look up the definition of rate, let's see what it says. Okay, so it says a measure, a quantity, or a frequency. A measure, by the way, is a number. Okay, a measure describes a magnitude which results in the name that we give to a number. Okay, so it's a measure, it's a number. So that's what we mean when we say rate. Okay, and so typically when we talk about a rate, we think of fast or slow, okay? Because, for example, in physics, we have speed, and we understand speed by comparing distance to time, okay? So that's how, did you get that? In physics, we compare distance to time. By the way, time is also a fixed distance, but you can read my article on LinkedIn called What is Time? And I'll place a link to everything, including to these pages and also to the applet that I'm going to use and any other appropriate detail in the detail section. So, excuse me. Now, this question here makes no sense at all after 3, but what they're asking you here, in effect, and there is really no correlation between the two. What they're asking you is, what is the slope of the distance function at t equals 3? That's what they're asking you, okay? So, as you can see here, well, this lecture is rather sloppy. He doesn't even state initially that this here is these here are the parametric equations. For example, x is equal to 500 minus 35t, and y is equal to 50t, right? And those are the parametric functions for distance. And from those, we can get the distance function, which supposedly is the hypotenuse in this case, because remember, car B and car A are going to be traveling in such a way that a hypotenuse will be between them all the time, and that is, by the way, the distance. But how fast is it changing? How slow is it changing? Is that even relevant? Okay, So now let's look at what's happening here. So what I'm saying is, rather than say, ask the stupid question, ask it this way: at t equals 3 hours, what is the slope of the distance function? Is it positive or negative? So initially we start off with the circle, and we know that z, but if we take z is equal to the square root of this, we have the distance between the two cars at a given time, at a given point, at a given xy, okay? And of course, if we do implicit differentiation, we get this, and if we get z on its own, the derivative with respect to z, then this is the expression here. So using this approach, the approach that this lecturer shows you, you will always have to know both x and y, and you will always have to recalculate the slopes for both those lines that I show you here, 500 minus 35t and 50t, okay? Both these derivatives will always have to be calculated, and you'll always have to work out the values of x and y. So we don't want to do that. So now, really what they're asking you is this. They're asking you, okay, what is the 3 hours? 3 hours, oops. Okay, so what is the slope to this blue distance function, which is given by this equation? I've narrowed the interval, but that doesn't matter. So the slope is given by the tangent line to this function at t equals 3. So all I've done here is I've parameterized, that's kind of a hard one, the distance functions, so that I'm working exclusively in terms of t. And that makes it much easier because I can differentiate this function to get this red function down here. And all I have to do is put 3 into this derivative, and it will tell me that the slope is minus 14.96963, which is the same as what is found over here. And what I'm going to show you now is that first of all, let me just say a few things before I continue. This blue point here is not on the circle path, which is this dotted path. And of course, it doesn't look like a circle because I've changed the axis so that I can show you all the details. Okay, so this blue line is not on the circle axis, and it's not at the vertex of this parabola, which is in fact the distance function. Okay. In fact, it's not strictly speaking a parabola, but it looks like one. So that's the first thing. And then the next thing is to try to understand this in any other way, like for example, the way these fools in the mainstream are telling you. What they're saying is you start off with car A here, west of car B, which is over here, car B, yeah, which is over here. The distance is 500 miles, and they tell you that car A moves towards car B, and car A will move strictly south. So when we move along like that, this is what happens. We have this red hypotenuse here, which is the distance between car A and car B down here, right? So now what they're asking you is how fast this distance changes. But this, how fast it changes has nothing to do either with the circle or with the movement of the cars, because it takes into account both the speeds of the cars and creates a distance function. So what normally when we differentiate distance function, we get speed, and it would tell us the speed that an object which moves according to this distance function is given. But what is moving at this speed here? If this is a speed, like for example, after 3 hours, what is moving at that speed? Can a distance be moving or changing at that speed? That's just nonsense. It's changing. How can you say a distance changes at a certain number of miles per hour? That's just absolute rot. And then, of course, what these fools constantly go on about is the instantaneous rate of change. By the way, there is no such thing as an instantaneous rate of change. And if you go to this video here, which I debunk everything about instantaneous rate of change. This moron that you're looking at here is Professor Gilbert Strang from MIT, who's one of the chief propagators of this bullshit theory. So I'll place a link there too, and you can see that there is no such thing as an instantaneous rate. Okay, so but basically when they say instantaneous rate in the mainstream, what they mean is the slope of the tangent line to a particular function. It doesn't even have to be a distance function, in which case it's not the speed. So fast and slow is not relevant. Okay, it's just absolutely incredible how stupid are mainstream academics. And by the way, they're not getting this which I'm telling you. What I'm telling you right now is not understood by mainstream baboons, because they simply are, their heads are too far up their rear ends to be able to smell anything but their disgusting whatever. What I'm telling you right now is truth, okay? It's fact. I'm giving you the absolute facts. I don't know why there's a 1 up here. This is strange. Anyway, it's probably just an error in the way the latex is working. This 1 here shouldn't be here. Okay, so now, and there's no such thing as an instantaneous rate or a rate at a point, because the difference quotient, by the way, is irrelevant at a given point. Do you understand that? So anybody who might tell you, oh yeah, we use calculus to do everything, to build computers, that's garbage. We don't use calculus at all for that. We didn't use calculus to go to the moon. The measuring devices on all the space vehicles, etc., they do not use calculus. Okay, they use something called a difference quotient, and it's not accurate because in order to be completely accurate, there would have to be a mathematical model like the one I'm giving you here, this blue function, which is a distance function. Otherwise, you cannot have something that is equivalent to what they think of as the speed at a particular instance. It's not the speed at an instance, it's the speed at a given time or a given place. Okay, it's got nothing to do with instantaneous nonsense. The word instantaneous should just be tossed right out of all calculus. It has no place. Okay, it doesn't mean anything. But when they use it, that's what they mean. They mean the slope of a tangent line at a given point, because you cannot use calculus if you do not have a mathematical model. All right, so now I've shown you 2 parts here. I'm going to summarize because I'm running out of time. I've shown you 2 parts. In the video, in the lesson here given by the lecturer, he shows you how to do it for only one particular pair of x and y. In other words, if x is 35 miles an hour and y is 50 miles an hour, and each time you'd have to use this implicit differentiation to find the function. But I show you that that's not the best way of doing it, because then you have to do it every time. But here, all you need to know to find the slope at a given time, not the rate of change, that's bullshit. The slope at a given time, you just plug the value of t in this equation down here, because this is like the speed of a particle which moves according to this blue model here, okay? According to this blue model. That's what it's saying, all right? Nothing else. Okay, so that's what I wanted to show you in this video, and so that should give you an idea now what rates of change are about. And of course, obviously, if you have a lot more functions than 2, the parameterization may not be that simple, in which case you could either resort back to implicit differentiation, or you could figure out a way to build a far more complicated model. So that's all I have to say for now. This is the New Calculus channel, and I'm John Gabriel. Please subscribe to the channel, spread the news, and hopefully, I'm totally out of breath again. I'll be back someday with some more interesting information, debunking the myths of mainstream mathematics. Till next time, goodbye.